All right, here to cover another thing I worked on. This is probably the last rudimentary system I'm working on before actual gameplay things will get produced, right? And so the goal was to make extremely fast pathfinding for lots and lots of agents. During the jam, I was able to support, a fair amount of agents. I would say like 50 wasn't very slow. Um, but there were two problems. One, any more than that, my pathfinding took a long time to find them. And also, the paths were completely static in the jam I was making, to where like I wasn't able to support enemies that maybe could break walls, right? Like if I wanted a boss enemy to smash through the player's fortifications, the paths would never update, right? And so what I've done is I have made a system that supports that, right? And so um, yeah, that's what I want to cover today, right? And so there's two facets of what I'm covering. Is one is how am I pathfinding, right? And then two is I guess there's three parts. The second thing I want to cover is how the agents are made to path, right? But that'll be very quick. And then I want to also cover some of the loose optimizations I did that can be applied to most things that you code, right? So this can be applied to any system made by anyone ever, these optimizations. So really, these are things that you could take note of, right? And so I'm going to go over a little bit of how I'm doing pathfinding. And so the first thing I want to talk about is like pathfinding algorithms. So what I'm doing is a variation of A star, right? And so A star relies on having a graph. A graph consists of a bunch of nodes, a bunch of nodes in space, and of course a bunch of edges, right? And so you have all these edges. Let me just draw them dashed. You know, so the way A star works is you take a graph of the sort, right? And you have a starting point. We'll call this the start, and an ending point. And so let's say each of these edges has some sort of arbitrary edge weight, right? So we have like 2, 1, 3, 2, 1, 1, 2, 3, 4, 5. And so the edges are aligned with the cost, right? The cost of taking that edge walking, right? So it costs our agent 2 to walk this top path from the start and 1 to walk the bottom path. And so A star is trying to find the lowest cost path to take, right? Well, actually, this is more in line with what Dijkstra's does, right? So Dijkstra's will explore forward using the lowest cost possible. So it'll say, okay, we know that this edge has a cost of 1. And so we take some notes along the way of like, have we visited the node? What is the lowest cost, right? So the lowest cost we visited this one with is 1. We have other notes along the way, and then we sort of sum those up, right? So this one has a 1, this one has a 2, and then as we visit here, this could either have a 3 if we come from 2, or a 2, so the minimum is 2, right? This one could have a 5, right? If you go 2, 3, 5, or it could have a 1, 3, 4. So 4 to get here. And then, so then you have 1, 3, there's a 4 to get here. This one is also going to be a 5 if you take a roundabout path. And then you have 8 and 9, right? And so the 9 is bigger. And so now you do a trace back, right? How did we get this shortest value of 8 here? Well, the path we took was we take 1, 2, 1, like these paths here, right? And so that gets you a sum of 1, 2, 1, 2, 3, 4, 8. And so that is how Dijkstra's works, right? And Dijkstra's is Dijkstra's will always get you the most optimal path because it calculates every single way. And so what I'm doing that's a little bit different from Dijkstra's is these edge weights are the same. In my game, I think I might even take the weighting out because I think every edge in my game will have the same weight no matter what, because that's just how the mono spacing of a block placing game works, right? Everything is equally spaced apart. But what I'm doing is slightly different. One is the second I reach the end node, right? The second I get here, I say, yep, that is my path. Okay. And so that means our algorithm has to do a lot of guessing, right? And so we want our guesses to be relatively accurate. So we're not only just going to take the smallest edge, right? Because this could be like, oh, well, if we take the smallest edge every time, we'd go like here, here, what? We might even go here, and then back to start. Well, that's wrong. And then so we'd guess here, and then we'd guess here, and that's wrong. And then we guess here, and then like there, and so we get there, right? But there's a lot of extra guessing there. And so A star takes into account one extra thing, which is called a heuristic. And so a heuristic is, pardon my writing, but a heuristic is essentially a way of guiding the guess. So it is a approximation of what makes a choice more correct. So we're going to take into account with each step, we're going to take into account the weight plus a heuristic. And so the easiest heuristic I came up with, which is probably not always the best one, depending on how complex the graph is, but you can only do so well, right? The weight plus the heuristic. The heuristic I came to is how far is the node from the end node, right? So the distance here is x. Actually, I also draw to the straight line, right? So the heuristic I'm adding is the raw space distance between the node and the end point, right? And so you see here there is, certain ones are closer than others, right? And so as you guess along the way, you'll take the edge weight in mind. And so let's say that both this node here and this node here are equally far from the end, and I didn't draw it a little slanted. You'd say, okay, well, we're going to take 1, right, because it's the shorter edge weight, and these two are the same distance from the endpoint. And now, will we take 2? Will we take this 2 or the 3 here? Well, we would take the 2, but 3 is much, much closer to the endpoint. So we're going to take 3, right? And then as we get there, we go, okay, well, it's either 2, which goes backwards, or 5, which gets straight to the end. And so then there's a balance there between how strongly you weight it towards following your heuristic, or how much you value the edge weights, right? And of course, in scenarios where it takes the wrong path, like let's say there was a, let me scribble here. Let's say there was a node out here, right? That didn't have a dead end, but this was also edge weight of 1, and it's pretty close to the end, right? We might go here, but of course, if this ends up being a dead end, which it is, it then walks back to its most recently visited, finds a new way to go, and that is it, right? And so I have done a lot of work to make this really fast, right, in the way I do it. And so there's things called a priority queue, and so I implemented my own version of that fits exactly the data that I'm using. And so like when a node goes here, right, we enqueue all of its neighbors into this priority queue, and their priorities assigned to the weight plus the heuristic, and that's the order we compute, right? So we'd have this array. It would say 1. It would say, let's number these, right? We have node 0, 1, 2, 3, 4, 5, 6, right? So we'd enqueue, okay, we need to visit node 1 and then node 2. But then, based on that priority, right, we then, as we visit 1, we add its neighbors, right, and their priorities, right? So then, as we get here, we might say, okay, well, now actually we want to visit, we remove 1, right? We want to visit, now it's like 4, 5, 2, right? Maybe that's the priorities, the way it ends up. And we keep visiting that until we've reached the end node, and then we return the path based on a trace we do, right? And the trace back, I'm not going to describe how I keep track of that. But the point is that we are prioritizing nodes to visit, and all we're doing is repeatedly adding nodes with those priorities to this list. And so I'll go over a little bit of what that code looks like, but I probably won't delve into it extremely in depth, right? But we'll talk just a little bit about what that looks like here. And so we have in this class here a graph node. So there's not a lot going on in the graph node, but we have what I would say is all the data we need. That's all it is. We have the position of the node, which is used not only for doing the pathfinding later, but also it is used for computing that heuristic. We have the quantized position. This is used for quick lookups from the graph, right? And quantizing is essentially taking space and sectioning it out, right? And so this node is in this square of space, right? And so that allows us to do quicker lookups than looking through every node. We say, we were looking for nodes that are in this section only. We have the list of neighbors, so all the nodes that this one's attached to. We have the graph index, which is used for also quick algorithmic lookups, right? So when we initialize the graph is an array of graph nodes. The graph node knows which index it is in that array, and that helps for quick lookups. And then enabled, right? And so we're able to enable and disable nodes at will. And so everything else in here is just setting and getting those things. And then a graph has a lot of utility functions in it, but at the end of the day, it is a list of nodes, right? And we add to that list. I don't have removing in, and the reason I'll say that is, I'll explain that in a minute, is because the way that I'm creating these graphs is extremely fast. And so it front loads all the labor, and then pretty much nothing else happens later on, right? But there's a bunch of helpful, utility methods here for computing neighbors of nodes, getting which node on the graph is closest to where you want to go, and then finding a path based on pathfinding. And so we'll go a little bit into the pathfinding here. It's a complicated algorithm, but it does essentially what I was talking about, where it has all of these tracker things it does along the way. It's tracking lots of values for every single node, right? And so we do a lot of indexing via that graph index we're looking for. And so all the things we track are like, how do we get to the node we're at? How far is it from the start? This is the priority queue that I custom created for this. There's a depth tally, which helps me track how many steps it was to get there. That is so I can get the length of the resulting path. And then the visited run, this is the way that I'm reducing or completely eliminating the need to reinitialize these lists, right? So I keep track of if we visited a node, and then if we visited that node, which shortest path check are we on, right? So is it the run we're currently on, or is it a previous run? And if it's a previous run, we overwrite the value. If it is the same run we are on now, then obviously we've already visited it. And that prevents us from ever having to reinitialize these, and that prevents a lot of GC shenanigans, right? And so it's a lot faster that way. And we'll talk about that at the very end. I'm not going to talk about it, but yes, we look at each neighbor of the node we're at, we add them, we add all the data to the lists, and then if we've reached the end, we can compute backwards, right? I'm not going to dive into it too much. I'll zoom in so that I can explain a little bit more later in the optimizations. But now I want to take a look at sort of how I'm constructing this, how would you call how I'm constructing the grid here, right? And so let me go into my grid constructing class, and I will turn on, I suppose, the drawing, and I will remove that line that clears things. And so what you'll see is, I got to refresh the assets here. What you'll see is that I create the graph at the start with every single node that could ever possibly be enabled in it, right? So all these grayed out ones, they are disabled, but they are potential places for nodes. And the reason that helps is because with pushable blocks like this, and you'll see here if I unpause and push something, you'll see that this node here goes from white to gray, and this one goes from gray to white. So gray, white, white, gray. And so what that does is it allows me to never have to create new nodes. I never have to move nodes. I never have to recompute neighbors ever. The entirety of all possible graphs exists in this subset, and all I'm doing is disabling or enabling nodes based on the dynamic objects in the scene, right? And so that helps me compute live all the possible graphs, right, without having to ever recompute. And so that makes dynamic path changing, and if I turn off gizmos, you'll see it, dynamic path changing like this really fast, because the graph never has to say, okay, delete a node here. We're then going to add a node at this position. Now compute all of its neighbors. Make sure you add the neighbors of that node to itself and add itself to those nodes. And so things like this become really fast. It's nearly instant, right? So that's why I'm pre-computing every single node ahead of time. Okay. And so then all that I have to do is in all of my algorithms where I'm, solving the path, I simply check if the node is enabled. If not, I will skip it. And so there are a lot of extra nodes in the graph, and that does lead to unnecessary checks. The checks are practically instant, right? I just say, is the Boolean flag inside of this node that I'm looking at set? If not, don't do anything, right? And so there's not a lot of extra overhead there for a lot of extra performance when it comes to constructing the graph. And so now I'm going to talk just a little bit about how agents work. I have two things set up here. It's a little bit rudimentary because I don't have the outside systems set up yet. But what I'm doing is I have an agent service, right? And this agent service is what queues up, so to speak, all these agents. So what does an agent do? An agent has an assigned path. This is all for drawing right now. It'll go away when I'm done debugging. But an agent has an assigned path. It knows where it's at on that path. And then it just continually either follows that path or waits to be reassigned. So there's the initialize here. It's a little state machine, and this should help easily understand what's going on, right? We have a state where it's moving to a node. It sets some values for that. It does its stepping of that state, which moves it. And then when it's done with that state, it sets the next information, right? And then we'll either go to the end if we're done, or if we're just done moving, but it's not the last path index, we go right back to this state. It all reruns, including the enters and the exits, and we continue going, right? But the agent service has a concept known as pooling, right? And so for pooling, I'm sure most people know what pooling is, but we will draw it regardless, because that is what I plan to do for this. So when it comes to pooling, what you're saying is the reason that a lot of games tend to be slow is because one of the slowest things you can ever do when making a game is creating new things in memory, right? So spawning an object or deleting an object is really slow. And so what we do is we have this pool. And at the very start of the scene, we spawn a bunch of objects in the pool, right? You know, all these objects are created, initialized, and ready to be used. And so what we do, you know, blah, blah, right, is we simply spawn everything right at the loading of a scene. And then we say, okay, disable it all now. And so then what our object does is we have our agent service. Instead of saying, okay, instance, or create a new instance of an agent, what we do is say, okay, take a disabled agent from this pool, right? From this pool, enable it, you know, turn it back on, and then we'll use that. And so we set that. And so what that prevents is ever destroying things or ever creating things, which, like I said, very, very slow actions. And so this saves a lot of GC cycles, right? Because if you destroy a complex object like an agent that has lots of data on it, the memory of your application has to say, okay, release all objects with this reference, right? Release this reference, clean up the data, and then sometimes, I don't even know if the GC does this, but it might even vacuum the memory, right, to clear out all the data there and reset it as enabled, right, or available. And so instead of destroying things, we simply say, okay, throw that back to the pool, disable the agent, wait for it to be used later. And so this is how you really, really prevent heavy performance impact from things like this. And so you'll see this setup in, and I even hit diagnostics here. So you'll see this setup here, right? When we initialize, we simply spawn a bunch of agents and then release them from the pool, right? And releasing is simply disabling them. And then when we want to create an agent, right, we have this loop here. If it's time for us to create an agent, we say, okay, start the agent. And what does that do? It restores it from being released, right? It sets its position and it sets its path. And so that is the way that we instantiate things, but save on actual cost of instantiation. And so you'll see that when these, and I'll turn off the gizmos here, when these agents hit here, they're not deleted. They're practically just teleporting to the side because they get released, and then the spawner says, oh my god, we need to spawn another one. And so it's released, which is disabled, turned back on, teleported, and set to a new path, right? And so you'll see that this is much, much faster. And you'll even, if I did the profiler, which I guess I can show, you'll see that, I don't know if this will actually pop up correctly. Yeah, so you'll see here my script's the only thing that I'm profiling, running at about 1000 FPS. But if you look at the garbage allocation here at the bottom, nothing is allocating. There is no GC allocs at all while this is running. And why is that? It's because we're not ever creating or destroying anything. There's nothing for the garbage collector to have to collect on, right? So that's why it is absurdly fast. And so now I'm going to go over some of the basic optimizations I did, right? And I took this Pathfinder from for computing the paths of 1,000 agents, 1,000 agents at once, was about like 50,000 ticks, right? 50K ticks. And this on my computer, because I'm running lots of ticks per second, in at least in the Unity engine. I don't know what the actual tick rate is, maybe locked or whatever, but this computes about to maybe 4.5 milliseconds. And so that's not really that slow, but it's not as fast as I wanted it to be. So I went through and I did some basic optimizations, right? And so we talked about this loosely, but one of the first things that I came to, or I suppose that I realized I needed to come to, is that a lot of things needed to be cached, right? So I have a bunch of these data structures here, and you would think to yourself, well, this must make the computing much, much more complicated, right? There's so many tallies here that are just happening in arrays, and you have to index them with an index that is it's pulling a property from a graph, right? And so all these optimizations make it marginally more complex to compute, but it's much faster than the downsides. And so some of the downsides that I cut from, you'll see the two major ones I'm going to talk about is a scratch. A scratch is a buffer that you're using for computes, and then you write from that buffer to the answer, and you continue to use that buffer without ever creating anything new. So you'll notice only on the very, very, very first call of find shortest path do I ever set these. And I think this could go in some sort of, in some sort of class creation method. I don't even know why I'm doing it here, right? But point being that this is the only time that any of these things are instantiated. They're always reused. The only thing I'm ever clearing is my complex data structure up ahead or above that is essentially a priority queue. Every time you add something to it, you enqueue to it. Based on that priority you enqueue it with, it places it at the top, bottom, middle, wherever it belongs. But that is the only thing that I'm clearing along the way. Everything else is reused, and it's reused based on this which run are we visiting it on tracker, right? And so that prevents me, once again, from having lots of GC allocations, which we talked about, being slow, of me saying, okay, release all the memory for these arrays, and then give me some new memory for new arrays, right? And so that's very slow. So limiting as much as possible these new operators is really the game for optimizations when it comes to, especially like WebGL builds, but when it comes to any build, right? The GC is slow. And so that is like important thing number one, but actually the bigger optimization is using a scratch, right? So what I used to be doing before I had a scratch was at the bottom here, I would say, okay, let's get a path length. Let's create a new graph node array of that length and write to it, and then return that graph node array straight to the agent requesting it, right? And then that agent would then copy over the answer. It would not even copy over. I think it actually steals it as a reference, right? And so I guess like we've been talking about, allocating new things is slow. And so what the agent does is it has a permanent array that it copies to. This path array is initialized at the maximum possible length of a path it could have, right? And so at the beginning, when the level starts, right, the agent has what you would think is bad, right? It has this huge usage of memory that says, okay, we have a bunch of null nodes here, but this is the longest array you could ever need, right? So the agent pre-comes with an allocated array of the maximum number of nodes it would need. And then this array is full of nulls, right? And then the Pathfinder returns a span. A span is, so here is the Pathfinder's scratch array, right? It's also a bunch of data. It's not nulls ever, right? But it's written to as if it doesn't matter, right? But what it does is it keeps a counter, right? It has a count, and it says, okay, when we're finding a path, let's write from the base, right? So we're going to say, okay, everything from here out, this is count elements, is what the path we need to return is. And so it returns a span, and a span is a reference type. So it allocates no memory. A span is an array. It's an array and a count. And so we return this span, which is a very shallow reference type that is supposed to completely be demolished after its usage, right? And we return that to the agent. The agent copies from that span to its own pre-allocated array, and then it uses that, and that span leaves, but it never allocates, it never destroys, it's just no longer in existence, right? Because it's a reference type rather than its own, hard copy. It's a very, I think that's called shallow copy. Yeah, it's a shallow copy or whatever, right? And so all that the agent does is to say, okay, let's copy all these elements, copy 1, copy 2, copy 3, all the way up, and then bam, this span is gone, nothing allocated, nothing lost. And so that's how I'm completely avoiding GC checks, and it is making this pathfinding. It went from about 50,000 ticks with just these two ideals of not reallocating ever the arrays in memory that I'm using for computing, and not ever reallocating to the agents. The agents never set a new graph. The Pathfinder never sets a new graph. Nothing new ever happens. And so that's how I took it from 50,000 ticks per to about 8,000 ticks, which is less than 0.5 milliseconds, per, that is a horrible M. It's less than 0.5 milliseconds per run, which is absurdly fast, which means I could now host 5,000 agents or so, probably even more, for the exact same speed I used to get 1,000. And so I could never host 5,000 agents in the past. That would be way too slow. That'd be nearly 30 milliseconds. Like 5 milliseconds, not that noticeable. 30 milliseconds, you would notice a significant drop in performance when you have to recompute all those paths. Of course, this is a bit overkill on the engineering side because I don't think I'll ever have 5,000 agents all recomputing at once in the game, right? Because these agents will be getting released regularly when they're killed by towers or whatever. But point withstanding that now I could, right? And so that is the whole point of this. And now that I have all this boilerplate out, it'll be enough of the boring engineering videos I'm doing. And hopefully by next weekend, maybe the following, I'll have more gameplay oriented, exciting devlogs of like, maybe I'll have some towers implemented and I'll talk about how I'm handling, hit frames, other things. I have some shader ideas I want to work on. But this had to happen. This boring engineering had to happen first, right? Otherwise, I couldn't support all the ideas I want to do in this jam rework, right? So yeah, this is hopefully the last boring, I optimized some stupid shit engineering video. And it'll end up being more from this point onward of gameplay introductions, demos, and me just yapping a little bit about maybe a tower I made or something, right? And it'll be much shorter, much less drawn out, much less explaining my process. But I did want to still talk about this because this was actually really fun to optimize. It was always fun to test, really stress testing these systems that I'm writing. It's a lot of fun. I had a good time doing it, so I wanted to share some of the process, some of the things that I overcame, and what those hurdles I found along the way were, so that I could make this as performant as humanly possible, right? Anyways, thanks. Bye-bye.